In previous videos, we've seen how you can model the motion of an object with a position versus time graph. And then we've also seen how you can use a motion map, which is a little bit more realistic way of modeling motion for an object. Today we're going to look at a third way of modeling motion that focuses on velocity and time rather than on position and time. So this is called the constant velocity, or velocity versus time graph for constant velocity particle model of motion. And it's actually a super useful tool, especially when we start looking at more complex kinds of motion later on. Imagine a car that's driving on a freeway with the cruise control set at 60 miles an hour. If we were to make a graph of the speedometer reading every 15 minutes, it would be a pretty boring graph because the speed never changed. But there's a useful thing about this graph that makes it worth examining for a bit. If someone asked you how far a car would travel if it went 60 miles per hour for an hour, you'd probably say, well, obviously it went 60 miles. How far would it go in 2 hours is not much harder, 120 miles. A half hour? You probably know the answer for that one too. Now let's go back to the graph and see where the calculations that you make in your head can actually be seen in the graph. For example, the 1 hour. Why did we know that that was 60 miles? If you think about this graph and you sketch in kind of an area under the graph between the 60 and the 0, that's 1 hour wide, and take the area of that, the length times the height, or the width times the height here, it's 60 miles per hour times 1 hour, and that's where you get 60 miles. Let's look at the 2 hour situation. Again, let's sketch in that area, and then let's look at the dimensions. Now it's 60 by 2. So 60 miles an hour times 2 hours is 120 miles. Let's look at the half hour. There's our area. Here are our dimensions. And when you calculate the area, you get 30 miles because it's 60 miles an hour by a half an hour. So you see the pattern here? What we're talking about here is a tool that we can figure out displacement from. The area under the graph of velocity versus the time is the change in position. Now this is a positive graph, and so it's easy for me to say the area under the graph because it's easy to visualize going from the 60 down to the 0 point. Now it's possible, of course, for velocity to be negative, and so when we say under the graph there, what we actually mean is above the graph because you have to go back up to the 0 line. When you start doing some problems, you'll begin to see situations like that. Just keep that in mind. This idea seems a bit silly because it's super easy. You're just finding the area of a rectangle. But when we study motions that get more complicated, it becomes a super powerful tool. So to set up for that, let's explore how to translate position versus time graphs to velocity versus time graphs. The key to translating a graph of position versus time to a graph of velocity versus time is slope. Since the velocity is the slope of a position versus time graph, or x versus t, when you graph velocity versus t, you are indicating that slope. When the motion is constant velocity, the lines on a velocity versus time graph are always going to be horizontal lines because the velocity is never changing. In constant velocity particle motion, CVPM, which is what we're considering here, there are really only 3 basic shapes that we can have to translate. If the object is moving forward, the slope of position versus time is constant and positive. So the horizontal velocity versus time line is above the 0 line and constant. So if you were to figure out the displacement, it would be the area between the red line and the 0, and that would be a positive displacement. If the object is moving backward, the slope of position versus time is constant and it's negative. So the horizontal velocity versus time line is below the 0 line. And so if you were to find displacement, it would be above the red line and below the 0 line, and that would be a negative displacement. And the last possibility is kind of a trivial one. If the object isn't moving, the slope is 0, so that means the velocity versus time graph would just be a line at 0. To make the graphs quantitatively accurate, you'll have to actually determine the slope. So let's try a couple of examples. This graph shows an object that starts at a position of 30 meters, and it moves to a position of 100 meters in 10 seconds. So this makes the slope easy to calculate. The change in displacement, or the change in position, which is the displacement, is 70 meters. The change in time is 10 seconds. So the velocity is the ratio of those two, and that works out to 7 meters for every second. It's a positive velocity and it's constant. To make the velocity versus time graph, since the velocity is constant at 7 meters per second, we just draw a constant horizontal line at 7 meters per second. So you can see we're above the 0 line because it's positive direction of motion, and it's right at the 7, right between 6 and 8. Now let's try one in reverse. This graph represents an object that's moving backwards at 2 meters per second. This is a velocity versus time graph. It's important to read that vertical axis to look at what kind of a graph are you actually talking about here. So this is velocity. It's constant at negative 2 meters per second. It's going backwards 2 meters per second of speed. This means that the slope of the position versus time graph must be negative 2 meters for every second. So this would be going backwards 20 meters in 10 seconds. So here I've drawn a position versus time graph that starts at 100 meters and drops 20 meters back to 80 meters, and it does it over the course of 10 seconds. So that is a position versus time graph that matches this velocity versus time graph because it has that slope that's indicated by the velocity. Now, I picked a starting point of 100 meters, but there's nothing in the velocity versus time graph that tells me where the object actually started. In fact, any position versus time graph that shows a line parallel to the one that I drew is equally good because velocity versus time graph tells us nothing about where the object started. It can't tell us position, but it can tell us displacement or change in position. Really, the fundamental thing that we've learned in this that's most important that we'll carry on through our study of motion is that the area between the velocity versus time graph and the 0 line is a representation of the displacement. So it's easy to find area of a rectangle, it's length times width, so it's easy to find the displacement if you have only velocity versus time graph to work with.